One of the most common ways in which a quantity can grow is exponentially. We can describe processes of growth using exponential functions. These functions are only approximations to the real world. They can help us understand it and make predictions about it. If you're watching this video, you're probably already familiar with exponential functions or equations. I've covered these in more detail in my other videos. Almost everything in our world grows from something. People, organisms, crystals, animals, or economies are all examples of things that grow. This video is focused on exponential functions that are increasing, which is called growth. I've covered decay in more detail in another video. An exponential function is a function with a power in which the variable appears as part of the index or exponent. These are all variations of exponential functions. If b in these functions is greater than 1, the function is increasing and we have growth. Real-world examples of growth include compounding investments, growth of bacteria, or population growth. Consider $5,000 invested at an interest rate of 5% per annum compounded annually for 3 years. Let FV be the future value and N be the number of years. The $5,000 is increased by 5% at the end of year 1 when N equals 1. To increase 5,000 by 5%, we multiply it by 1.05. After 1 year, we have $5,250. In year 2, the new value is increased by a further 5%. This is the same as writing 5,000 times 1.05 times 1.05, or 5,000 times 1.05 squared. After 2 years, there will be $5,512.50 in the investment. In year 3, the new value is increased by a further 5%. This is the same as writing 5,000 times 1.05 times 1.05 times 1.05, or 5,000 times 1.05 to the power of 3. After 3 years, there'd be $5,788.13 in the investment. From this pattern, we can see that the future value of the bank account after n years is 5,000 times 1.05 to the power of n. Here's a graphical representation of the future value of the investment after n years. We expect that the bank account will grow in a smooth curve rather than discrete jumps. We therefore expect it will be given by the exponential function. Future value equals 5,000 times 1.05 to the power of n. You'll notice that the function is increasing or growing in this example. The future value of an investment is given by FV equals 14,000 times 1.09 to the power of n, where FV is the future value and n is the number of years. What's the original value of the investment? So that's when the number of years equals 0. So we substitute that into our formula and we solve and we go 1.09 to the power of 0 is 1, anything to the power of 0 is 1. And we find that the original value of the investment is $14,000. What's the value of the investment after 5 years and 15 years? First, let's look when n equals 5. So we substitute that into our equation and we solve and we say that the value of the investment after 5 years is $21,540.74. The value of the investment after 15 years, when n equals 15, is 14,000 times 1.09 to the power of 15. We get the value of the investment after 15 years is $50,994.75. Let's continue with the same example. Let's graph the future value of the investment over time. Here I've graphed the equation. I've showed techniques on graphing exponential functions in my graphs of exponential functions videos. Have a look at that if you need help graphing the function. Use the graph to find how long it will take the investment to reach $40,000. We're looking at the future value axis, which is the vertical axis. Here I've identified when the graph will reach $40,000, and that seems to fall just between 12 and 13 years, or just after 12 years. The growth of a new type of bacteria is given by B equals 1,000 times 1.15 to the power of t, where t is the number of weeks after the initial observation. What's the original number of bacteria? This is when t equals 0. We substitute into our equation, we go b equals 1,000 times 1.15 to the power of 0. Anything to the power of 0 is 1. And we work out that the original number of bacteria was 1,000. How many bacteria are there after 5 weeks? This is when t equals 5. We substitute that into our equation and we get b equals 1,000 times 1.15 to the power of 5. We can put that into our calculator and we work out that after 5 weeks there's 2,011 bacteria. We're going to continue with the same example. Let's draw the graph of the number of bacteria over time. So again, I've graphed it here. Please refer to my graphing video if you need further tips on how to graph it. How long will it take for the number of bacteria to reach 100,000? So we trace it on our graph, and we determine that approximately 33 weeks it will take for there to be 100,000 bacteria. That's it for this video. Thank you.